All right, welcome to this explainer. I want you to imagine we're all grabbing a seat in a first-year university lecture hall, getting ready to unlock what is honestly one of the most powerful concepts in human history, the calculus derivative. Today, we're going to absolutely demystify the physical meaning of the derivative. We'll start in the tangible, physical reality of falling objects, plunge straight into the abstract beauty of the math, and then pop right back out into the real-world engineering that literally powers our modern lives.
Here's our roadmap for today's explainer. 1. Velocity and pumpkins. 2. Secant to tangent. 3. Newton versus Leibniz. 4. The power rule. 5. Continuity and brakes. And 6. GPS and circuits. Let's jump right in.
Section 1. Velocity and falling pumpkins. Let's ground this in physical reality by looking at a pretty famous Halloween tradition over at MIT. Every year, students drop pumpkins from the roof of a building that's about 400 feet high. Now, this isn't just a fun mess to clean up later. It is actually the perfect physical model for understanding rates of change. The equation of motion for that falling pumpkin is its height, y, equals 400 minus 16 times time squared. So if we set the height to 0, it's pretty easy to calculate that it takes exactly 5 seconds for that pumpkin to smack into the ground. During those 5 seconds, it travels 400 feet, which means its average speed is 80 feet per second. But think about it. If you're a spectator standing right near the impact zone, you really don't care about the average speed, right? You want to know its instantaneous velocity at the exact moment of impact. And to find that, we absolutely need the derivative. By taking the derivative of our height equation, we get our velocity equation. Y prime equals negative 32 times time, t. If we evaluate that derivative at exactly 5 seconds, it gives us negative 160 feet per second. Guys, that's about 110 miles per hour. The negative sign there simply indicates the downward direction of the motion. But that right there is the physical power of a derivative. It captures a rate of change perfectly frozen in a single infinite split second. Section 2. From secant to tangent. Now, let's take that physical speed and translate it into geometric language to see what a derivative actually looks like visually on a graph. Because how do we geometrically capture that exact moment of impact? Well, this right here brilliantly illustrates the foundation of the math. Notice the green secant line connecting two distinct points on our curve, point P and point Q. The vertical side of that right triangle is the change in our function, delta f, and the horizontal side is the change in our input, delta x. This little triangle maps out what we call the difference quotient. It is the exact visual representation of an average rate of change. It's exactly like that 80 feet per second average speed of our falling pumpkin. But here is where things get really interesting, where the mathematical magic actually happens. Imagine point Q sliding down that curve, getting closer and closer to point P. As the horizontal distance between them, that delta x, shrinks down to 0, the green secant line transforms. In the limit, it becomes the red tangent line. The slope of that red tangent line is the derivative. It touches the curve at exactly 1 point, giving us our precise, instantaneous rate of change. Section 3, Newton versus Leibniz. As we push a little deeper into the math, it's pretty important to remember that calculus is a developing language and it has different historical dialects. The two main giants of this field developed totally different ways to write all of this down. On one side, we've got Isaac Newton, who used the very efficient prime mark, like f prime of x. It's incredibly fast to jot down. On the other side, we have Gottfried Wilhelm Leibniz, who much preferred the fractional notation, dy over dx. Now, while Newton's is definitely quicker for a chalkboard, Leibniz's notation is profoundly useful because it visually emphasizes the geometric truth we were just talking about. It reminds us that it's the ratio of the change in y over the change in x, as that limit approaches 0. Basically, it reminds you that a derivative is, right at its heart, a fraction. Section 4, Deriving the power rule. Okay, so we've got the core concept down. But how do we actually compute these derivatives for common functions without having to draw out secant lines every single time? For instance, how do we systematically handle power functions, like x to the power of n? Well, we use the power rule, and it's actually something we can prove systematically. First, we plug our function, y equals x to the power of n, right into our difference quotient. Next, we expand the term x plus delta x to the power of n using the binomial theorem. And when we do this, the initial x to the n terms beautifully cancel each other out. What we're left with is a single term containing delta x alongside a bunch of other terms with even higher powers of delta x. Step 3, we divide everything by delta x. And finally, we take the limit as delta x approaches 0. When we do that, all those higher power terms just completely vanish, and that big abstract limit elegantly collapses into the simple, beautiful power rule, n times x to the power of n minus 1. Moving on to Section 5, Continuity and Breaks. Now, if we're treating this like a first-year lecture, you absolutely have to learn that this powerful mathematical tool has some strict boundaries. A derivative does not just magically work everywhere, on every single function. For a derivative to even exist at a specific point, the function has to first be continuous at that point. Continuity basically means that as you trace along the graph and approach a specific point from either the left or the right side, the limit you are approaching is exactly equal to the actual value of the function at that exact spot. Simply put, there can't be any missing pieces. Comparing these two graphs, you can really clearly see the difference. Over on the left, we've got a smooth, unbroken, continuous curve. You can easily imagine drawing a tangent line anywhere along that path. But, contrasted on the right, we have a very sharp jump discontinuity. Sometimes graphs have a missing hole, or they shoot off to infinity at an asymptote, or, like in this case, they just completely jump values. At the exact moment the graph breaks, calculating a tangent line is utterly impossible. You simply cannot find a rate of change where the fabric of the function itself is torn. So remember, continuity is a strict prerequisite for differentiation. Section 6. Real-world applications. Let's bring this all back down to reality. We started with pumpkins, we worked our way through abstract geometry and limits, and now let's actually see how these concepts power the modern engineering world all around us. Derivatives represent instantaneous rates of change everywhere. Look at an electrical circuit. Current is simply the derivative of electrical charge with respect to time, dq over dt. Or look at thermodynamics. How heat flows through a wall is determined by the temperature gradient, dt over dx. And let's consider the GPS in your phone. Satellites send signals with slight measurement errors, right? Engineers use derivatives to calculate the precise sensitivity of these measurements. Specifically, they look at how a tiny error in the satellite altitude, delta H, impacts the accuracy of your location on the ground, delta L. Without calculus, your phone's map wouldn't have a clue exactly where you are. So, the absolutely crucial point here is that calculus isn't just some set of abstract formulas you cram into your head for an exam. It is literally the language of change in our universe. From a pumpkin shattering on the pavement to the invisible radio waves guiding your car, derivatives allow us to quantify the exact nature of the world in motion. Which really leaves us to wonder, as you look at the moving, shifting world around you today, what hidden rates of change will you try to uncover next? Thanks so much for joining me for this explainer.